Welcome to your Unit 7 review on exponential functions. I'm going to scroll through and show you everything I'm going to go through as well as the formulas you need to know. If you want to pause the screen for a minute and just copy down all the formulas that I have written down and little notes and things, that would be good. One thing I will point out that we don't make a huge deal about, but it does come up sometimes. If you are doing compounding continuously, typically we're talking about compounding continuously in terms of growth, but it has come up where we have compounding continuously as a decay function, and in that case that would just mean the r is negative. And that's because e to the negative 1 is 1 over e, which is a base which is less than 1, which then creates the decay portion of the function. So just be aware, it does exist. You can have continuous decay, but those are the formulas. These are the problems I'll go through, and you'll see I actually added in a couple little things. Alright, so starting with question 1. The table below gives the value of the Smiths' home over the last 25 years. Round to the nearest hundredth where necessary. Using your calculator, find a function that models the data in terms of annual growth. Usually we'll say find an exponential regression equation on your test, and that's how the Regents will say it as well. So this is going to be an exponential function, which means that when I do the regression, I'm not going to put the years in for L1, I'm going to put in years since 1990. So I'm going to call 1990 0, which means 95 is 5, 10, 15, and so on. So years since 1990. Now I go to my calculator. You go to Stat, Edit, and then L1 is going to become your years. L2 is going to become the house values. So now I hit Stat, Calc, and then I got to scroll down to find exponential regression. You'll see that I have my X list is L1, my Y list is L2. I should not have a frequency list, so make sure that's cleared. And then hit Calculate. And there you have it. Where did my work go? 1 second. So weird how that disappeared. Okay, so that's my exponential regression equation. So it says round to the nearest hundredth, so we're talking 82813.29. Times the base of 1.01 to the x, so y equals. Okay, so y equals that. That's my equation. Keep in mind this is an annual growth rate, so what this is saying is our house is growing 1% per year. Assuming this trend continues, use your equation from part A to approximate the house's value in 2025. So what you need to do is figure out how far 2025 is from 1990. Or you could even look out over here. Okay, 2015, then there would be 2020, 2025. So that's another 10 years. So from the original, that's 35 years. Okay, so that means we're just plugging x in for 35 in the original equation, and then rounding. So I'll leave that for you guys to do. You just plug it in your calculator. Alright, rewriting each of the following in radical form. Keep in mind the whole power over root idea. So power root, this is the 5th root of technically y to the 1st, which you may or may not see that with the 1. Most of the time you're not going to see it with the 1. The 4th root of 14y squared raised to the 5th power. Okay. With the negative exponent, that creates a reciprocal. Now it's a positive 1/3. Then this is 1 over the cube root of 4r. And yes, technically you would want to rationalize that, but this is just a rewriting exercise. Now in this problem, just the w is being raised to the 2/7. This is 10 times the 7th power of w squared. Okay, just the x is being raised to the negative 1/2. So this is 4 over x to the positive 1/2, which is 4 over radical x, so square root of x. And just for sake of you do know how to rationalize stuff like this, if this were a multiple choice, you may see it stated like this instead, with a rationalized answer. Okay, but it's just practice rewriting with those radicals. Now I added an f up here just to discuss what happens when you have a fractional base raised to a negative exponent. When it's a fraction, you can just simply flip the base, and now it's a positive 2/3. This is the cube root of 27 squared. Cube root of 27 is 3. 3 squared is 9. Now for each of the following, I'm giving you models in terms of x years, which truthfully I should have included in the directions. That's why I have it written there. We're going to talk about the initial amounts and the yearly rates of growth or decay, okay, to the nearest percent. So let's just get this out of the way. Any coefficient that you are seeing that I'm highlighting in green, those are the initial amounts. Done. That's it. Now, anytime we're talking about rate of growth or decay, we're looking at the b value so long as this outside exponent is a 1x, because 1x is representing 1 year. So, here's my b value. That's my decay factor. And I know it's decay because it's less than 1. What I'm going to do is set that equal to 1 plus r. Subtract 1. Now, technically I'm getting a negative, but I just ignore the negative when I talk about the percent of rate of decay. It's really just the difference from 1 there that helps you find the rate. The negative is just reinforcing that this is a decay function. So we are decreasing by 25% per year. Now the next one's a little bit trickier because I don't have a 1x on the outside, I have a 1/3 x. So what I'm going to do is rewrite my function like this by swinging in that 1/3, and now my b value is 1.35 raised to the 1/3. So I go to my calculator. Okay, so that's my b value. Subtract 1, multiply by 100, because that's my rate, multiply by 100. Oh, geez. Gotta go up here and grab that. Times 100. Okay, so about 10.5%. So 11%. Increasing by 11% per year. Alright, next guy. Again, this isn't a 1x, that's a 2x, so I'm going to rewrite it like this. Again, forcing that outside exponent just to be a 1x. The b value is 2 squared, which is 4. When you subtract 1 from that, you get a rate which equals 3. Now, times 100, that's 300. So what this is telling me is my function is increasing by 300% per year. Okay, and I'm not going to do the last one. You just bring in the 3/2. Same idea. Okay. The equation f of t represents the growth in Matt's bank account in terms of t years. What is the monthly rate of growth to the nearest 1/10 of a percent? Okay, so when I read this function, I read it as you initially have $300, and then you are growing at a rate of 25% per year. And I know it's per year because they told me t was years. It doesn't want years though, it wants months. So I'm going to rewrite the function like this. I'm forcing the outside exponent to be a 12t because 12t represents 12 times a year, which is a month. But I can't just make it be 12t because that would change the function itself. So I have rewritten the inside as a 1/12. And that's fine because when those multiply back together, that's t, which means I have not changed the function, I've just changed the way it looks. When I care about the growth, I simply look at the b value. Go to my calculator, 1.25 raised to the 1/12. Okay, so that's my growth factor. I subtract 1. That's my rate, times 100. I don't know why the 0 is so hard to press sometimes. Okay, so to the nearest tenth of a percent, we're talking 1.9%. Per month. And again, it's per month because I readjusted it to be a 12t on the outside. All right, solving the next couple types of problems. I'll actually start with number 6 because these actually are two exponential functions. And they are exponential functions because the bases are numbers while the variables are in the exponent. Now, in this type of problem, your objective is to get the bases to look the same. So when I look at 1 over 36 and 6, I think to myself, I can rewrite 36 as 6 squared. To make it 1 over 36, it's 6 to the negative 2. So in doing so, looks like that on the left. On the right, that already has a base of 6. Now that the bases match, I can ignore the bases and solve the exponents. So this is negative 2x, because that's multiplication between those two, equals 5x plus 14, and then you're just solving like you normally would. Okay, and you're done. Coming on over here, this is technically called a power function. It is not an exponential function, but we put in our exponential unit just because it does seem to fit well. If you have a variable in the base, which is what you guys are seeing here, your objective is to isolate that base. So I would add over the 2. Now, you're trying to create an x to the first. So I'm going to raise both sides to the reciprocal power of 5/6. Okay, so these will go to 1. So this is x to the first equals, and now this is 64 to the 5/6. Which you could think of as the 6th root of 64 raised to the 5th power. Now, because the reciprocal has an even base, you're actually getting 2 solutions out of this, and I'll show you how that works in your calculator after. Okay? Well, the 6th root of 64 is 2, so this is plus or minus 2 to the 5th. 2 to the 5th is 32, so the answer is plus or minus 32. That's what x equals. Now, I'll show you why this is in your calculator. So what I'm going to do is go here, go to y equals. The left-hand side, I'm going to type in x to the 6/5 minus 2. On the right-hand side, I'm going to plug in 62. Now, I'm going to adjust my window a bit here just because I know I'm going to get some answers of plus or minus 32 here. So my x min, I'm going to make negative 50. My x max, I'm going to make 50. Now, I'm looking for an intersection at 62, so I got to make sure my y max is maybe like 100. Here we go. So what you're seeing graphed is x to the 6/5 minus 2, and there is y equals 62. And as you're seeing, there are 2 intersections. So I can do second trace option 5. Make sure I'm on the first curve, which I am. On the second curve. And as you're seeing, that first intersection is negative 32, y equals 32. So the solution is x equals negative 32, which is matching my algebraic solution. The other solution, if I were to find it graphically, would be x equals 32, which also would match my algebraic work. All right, coming on down to one that's a little bit more complicated, we're looking at something like 12. This is, again, a problem where we have the variable in the base. So we're trying to isolate that. So I would subtract the 2. And then divide by 3. Make sure you do that. A lot of students forget to divide by the 3, and then they get completely messed up. Okay, now your objective is to create an x to the first. So I'm going to raise both sides to the negative 3/2. So these undo each other to create x to the first, or just x, equals 9 to the negative 3/2. Now I'm going to practice my power over root rules. Oh, and I technically get plus or minus, because when I raised the reciprocal power, the denominator was even. So I get plus or minus 1 over 9 to the positive 3/2, which is plus or minus 1 over the square root of 9 cubed. Square root of 9 is 3. 3 cubed is 27, so plus or minus 1 over 27 is your final answer. Okay, coming on down to 14, use the property of exponents to simplify. Okay, first thought, I always rewrite these as fractional exponents. So 7/6, 5/12. That's power over root. Now, in order to divide exponents with the same base, we subtract the exponents. So I'm doing 7/6 or 14/12 minus 5/12, which is 9/12. Okay, and you could leave it like that. That is simplified with one base. Okay, write an exponential function that passes through B10 and C160 in terms of a yearly growth rate if the initial value is A and there's 4 years between B and C. Okay, I'm going to come up with a table of values here. They said the initial value is A, so that means when x equals 0, y equals A. Okay. And then they said that there was 4 years between B and C. Okay, so what this is essentially telling me is that I can tell that we are multiplying by 16, but that's every 4 years. So if every exponential function is of this form, where x is years, initially we have capital A. Our growth factor would be 16, but it's not every year. That's actually once every 4 years. So I'm making it x divided by 4. Okay, that would actually be a function that matches. Now, if this were a multiple choice, you might actually see it stated like this, where they bring in the 1/4, which is the same thing as the 4th root of 16, which is 2. So initial value of A, growth factor of 2 every year. So if you take 10 and you multiply by 2 4 times, you should then get 160. So let's see. And I do. Okay, an adult takes 400 milligrams of ibuprofen. Each hour, the amount of ibuprofen in the person's system decreases at about 29%. How much ibuprofen is left after 6 hours to the nearest hundredth? Okay, so they initially have 400, and it's decreasing by 29% each hour. Okay, so this is your straight up decrease function. A equals P times 1 minus R to the T, where I'm going to say T is hours. Okay, so we don't know initially how much, or final amount, I should say, but we do know our initial amount is 400. We are decreasing at a rate of 29%, so 0.29. after t hours. It wants to know how much ibuprofen is left after 6 hours. So all I'm doing is simply taking 6 and plugging that in for t. So I go to my calculator. Okay, so that's our answer. So to the nearest hundredth, 51.24. That's how many milligrams you'd have left in the system. All right, you deposit $16,000 in a bank account. Find the balance after 3 years for each of the following. So I'm not going to do these all out. I'm just going to show you guys which formulas you would use. An account that pays 2.5% annual interest compounded monthly. So that's 12 times a year. Here's your formula. Okay, so in this case, initially we've got 16,000. You just plug that in. R would be 0.025 because we have to divide this number by 100 in order to convert it to our rate decimal. And N would be 12, as I already previously wrote, because that's 12 times a year. Now it would be almost the exact same thing for the next problem, same formula, but quarterly means 4 times a year. Initial amount is still 16,000. Our rate adjusts to 0.0175. Lastly, if our account pays 4% compounded continuously, that's this formula. Where again, initially it's I think I said 16,000 before, 1,600. Our rate is 0.04, and that's it. Now, something I didn't mention for each of these, because it's consistent among all of them, is T is 3 for all of them. So just plug these all in your calculator and compare. So you guys can check the answer key on bits for that. Okay, a little bit harder though. Steve's current bank account has $2,750. Okay, so that's his final amount. If he made an initial deposit 2 years ago and the interest rate has been 3.5% compounded semi-annually, so that's twice a year, with no additional deposits or withdrawals, find the amount of money or amount of his initial deposit rounded to the nearest cent. Okay, so again, here's our formula. Final amount is $2,750. We do not know the initial amount, so we're going to leave that as P. We know the rate is 0.035. I just divided by 100. Semi-annually is twice a year. Now they said this was over the course of 2 years, so T equals 2 as well. Okay, so what I'm going to do is plug this stuff in my calculator and clean it up. Okay, so in order to solve for P, I'd have to take 2750 and divide by that number. So 2565.64. And that's how much money he initially put in the bank. Okay, for 22, as far as graphing these go, just go to your table of values. So plug this into Y1 and look at your table. I'll show you in a second. Transformationally, the x minus 4 means right 4. So we took our exponential growth function, y equals 3 to the x. It moved to the right 4 and down 2. So that means if we move down 2, that means the asymptote changed to y equals -2, because normally it's at y equals 0. So notice the scale here is by 2s. Lightly dash at y equals -2 a horizontal line and label it. That's the asymptote that this function cannot touch. So dash that in so that you're aware. The domain of every exponential function is all reals, and the domain is contingent upon the asymptote. So this will be -2 to infinity. Now I'll show you why, and I'll y by using our calculator. And there you go. So I'm not going to graph this and waste time in the video. You guys can just look at your table of values. But what you need to be aware of is as x gets smaller, you're going to see that eventually it starts saying that you're hitting -2. That's just because the calculator is rounding. It only has so many decimal places that it can list before it just essentially gives up and rounds it to -2. This is where I always say you need to be smarter than your graphing calculator. Okay? It will not cross y equals -2. Sorry, this calculator keeps messing up on me. Okay, so as you're graphing these, just make sure you pick out some nice points and then just make it approach -2 when it graphs it, when you graph it. So it should look something like that. Okay, next we're at 24. Scientists studied a 150-pound human body in the woods to observe how the body's mass decays at different intervals of time. They noticed that 87% of the body had decayed after 1 year. To the nearest thousandth of a percent, what is the percent rate it decayed by each month? Okay, so our function initially has 150 for pounds, decaying at a rate of 87%. So that's why I'm writing 1 minus 0.87. And I'll list it to the t, where t is going to represent years. And I'll clean this up a little bit. Okay, but it doesn't want years. It wants what the rate is per month. So I'm going to rewrite this, forcing the outside exponent to be a 12t, because that's going to mean 12 times a year, which is a month. But that means I need to balance this with a 1 over 12 on the inside. Okay, we only care about the b value now at this point. I'm doing 0.13 raised to the 1/12 in my calculator. Okay, so that's my new decay factor. I want the percent. So I subtract 1. That gives me the rate. I multiply by 100. So per month, to the nearest thousandth, we're looking at 15.635. Okay, so you are decreasing at a rate of 15.635% per month. To the nearest thousandth of a percent, what is the percent rate? It will decay over 4 years. Okay, so I go back to the original function, which was an annual model, but it wants over the course of 4 years. So that means my outside exponent is going to be t divided by 4, because that means once every 4 years. But that means I need to balance it with a 4 on the inside, because I need both of these multiplied back together to still give me t, because I'm not changing the function, I'm just changing the way it looks. Now I only care about this b value. Okay, so that would be my rate. Subtract 1, multiply by 100, 99.97, 9971. It's just practically everything, which would make sense. So over the course of 4 years, 99.971% of the body had decayed. Okay. Next for 25, if you're going to use your graphing calculator to solve these, again, graphically, what you're doing is plugging the left side of the equation in for y1, the right side of the equation in for y2, and then doing intersection in your calculator. So second trace, intersect. So I'll show you real quick what that looks like. Okay, so y1, y2, I'll do a zoom 6. And there you go. There's your intersection. There's your solution. So I do second trace, option 5. Now the solution is just the x value. So since the coordinate is 2, 3, x equals 2 is my answer. So I'm not going to waste the time in the video graphing this. You guys can pull some points from the table of values, but the answer would be x equals 2. Okay, so moving on down to 26. Explain how this can be evaluated, so negative 8 to the 4/3, using rational exponents that result in an integer answer. Okay. Explain needs words, so we're going to have to add a little bit of words to this. So using power over root, I'm going to rewrite this as the cube root of negative 8 to the 4th. So again, add some words here. Okay, now I know the cube root of 8 is negative 2, so I can rewrite this as negative 2 to the 4th. So I'm just rewriting this. I really should be using parentheses here. Okay, so negative 2 to the 4th. So then negative 2 to the 4th is negative 2 times negative 2 times negative 2 times negative 2, which is a positive 16. And that would be your integer answer. So again, when it says explain, add some words. So I'm just going to add a little bit more. So I would say I rewrite the expression using power over root. And the rest of that should be pretty self-explanatory. Okay. Determine the value of y. Okay, so my first instinct when I look at problems like this where I have mixed representations of numbers is how can I get them to look alike? I'm going to try and rewrite everything in terms of fractional exponents. So I can rewrite this numerator as x to the 5/4 and the denominator as x to the 3/5. Okay, I'm dividing numbers with the same base, so that means I can subtract the exponents. So I'm going to go ahead and do 4/5 minus 3/5, or wait, 5/4 I meant, minus 3/5. I'll math frac that. So 13/20. Now, since the bases are the same, we can ignore them, so here's where we're at right now. I'm solving the exponents. Now you could cross multiply and solve, or just recognize that these denominators are the same, so y must equal 13. And that would be your final answer. Whew, this is going to be a long video. Almost done. Okay, the number of rabbits, R of t, can be calculated by the following equation, where t is the number of months. Cannot emphasize again how important it is that you pay attention to what t represents. What is the yearly percent rate of growth? All right, well, first of all, I got to look at this guy. This is saying I initially have 10 rabbits, and we're growing at a rate of 25% once every 12 months. That's how I read that. Here's the good news. Once every 12 months is a year. So when it asks me for the annual or the yearly percent rate of growth, I actually already know it. It's 25%. I can just read that now from the problem. Now when it wants monthly, keep in mind month represents t, and right now it's in the form of t over 12. So I'm going to rewrite the function. Bringing in the 1/12 and keeping the 1t on the outside, because again, 1t represents 1 month. Okay, I go to my calculator, I do 1.25 raised to the 1/12. Okay, subtract 1. Multiply by 100. So to the nearest tenth, we're talking 1.9%. So our rabbits are increasing at 1.9% per month. Okay, almost done. I just got a few little multiple choice questions to talk about. Okay, if f of x is given where it's 3 times 5 to the x, determine the coordinates of the y-intercept if the function is defined as f of x plus 4. So this is just taking the function and shifting it up 4. That's all that's saying. Now you can use your graphing calculators, but I'm going to use my knowledge of exponentials to solve this. 3 times 5 to the x is an exponential growth function, and I know that because that b value is greater than 1. So, okay, I know it's going to rise from left to right. I also know the initial value is a, so that's 3, so that's my y-intercept. So I'm crossing at the coordinate 0, 3. So we'll say roughly that's what our function looks like. Now you're taking everything and saying shift it up 4. So if I'm adding 4 to my y's, the answer would be 0, 7 for my new y-intercept. Find the annual rate of growth to the nearest 10,000th for the amount of money accumulated if 6,000 is invested at an 8% interest rate compounded quarterly. Okay, so it wants the annual rate of growth. All right, so this is a little tricky here. Amount of money is irrelevant. We're essentially really committed to what this base is. Okay, so 1.02. But that's raised to the 4t, which is 4 times a year. We want 1 year. So I'm doing 1.02 raised to the 4. I brought that t in. Okay, so I get 1.0824. Okay, now that's the base, which is equal to 1 plus r. So if you subtract 1, that's 0.0824, which is answer 1. All right, last one. Does the function y equals 3 to the negative 0.5x represent exponential growth or decay? What is the yearly percent rate of change? Okay, so this... Sorry about that. That was really strange. Okay, so this is y equals 3 to the negative 0.5x. Okay, first of all, before even dealing with the whole the whole 0.5 thing, as soon as I see a negative in there, I think of that as 3 to the negative 1, then times 0.5x. 3 to the negative 1 is 1/3. So I already know it's exponential decay before even talking about the rate of change. So growth is out. Okay? Now, as far as the exponential decay goes, we're going to do 1/3 to the 0.5, or even just go back up here. Your b value is 3 to the negative 1/2, or 0.5. Okay, so that is my b value. I subtract 1, multiply by 100. Looking at about 42.26%, which would be option C. All right, that was a super long video. I am going to end it then, so good luck studying. This is a challenging unit, so I hope this video helped.